Swayam Prabha. Digital India. Educated India.
With this lecture, we will begin the week 4. We are going to look at the viscous compressible flow equations in this lecture. We are going to look at some basic concepts to begin with, and then we will move on to the governing conservation equations. Before we move on with lecture 16, let us look at the topics of week 4. We will be looking at the governing equations of viscous compressible flow at length, and then we will derive the compressible boundary layer equations. We will discuss about aerodynamic heating, and we will also have a look at shock wave boundary layer interactions. To begin the topic, let us try to recall that at supersonic Mach numbers, the aspect of aerodynamic heating is insignificant. As the Mach number becomes larger, that means as you move to the higher ranges of the supersonic Mach numbers into the hypersonic or hypervelocity regimes, then aerodynamic heating would become very significant. However, both aerodynamic heating, that is high vehicle skin temperature, and shear stress, that is high skin friction drag acting on the surface of the vehicle, becomes severe at hypersonic conditions. So, this is what we are taking note of over here, and this is a significant point which distinguishes the hypersonic and hypervelocity regimes from the supersonic one. This would become clear as we go along this week's course content, as we develop the equations which can address this issue. Often the more important parameters to check at the hypersonic conditions are, please take note of this, the maximum heat transfer rate given in watts per centimeter square, and the total heat transfer in terms of kilojoules per centimeter square at the stagnation point, that is the nose region of the hypersonic vehicles. That is the region which encounters maximum heating during atmospheric re-entry conditions. Having taken note of these points, let us look at the shape of the vehicle. Why should the shape of the vehicle matter, and matter more so at hypersonic Mach numbers? So, let us have a look at the shape of the vehicle, how it would make a difference. A hypersonic wave rider, it is conceived as a hypersonic cruise vehicle configuration. This is more of a slender configuration. It needs to have a high value of lift to drag for efficient long range cruise, and it has a slender shape. I already told you. These vehicles, they do not encounter very large wave drag, because if you have a slender shape, irrespective of the Mach number, the wave will not become a very strong bow shock or a normal shock, and therefore, the wave related drag may not be so high. The shocks formed around the body are very strong, but they are not of the detached bow shock kind. This should be bow formed ahead of the blunt shaped bodies. However, they experience considerable skin friction drag. So, if you have a slender body, the wave drag may not be so significant, but the skin friction drag becomes very, very large as your free stream Mach numbers become large. A strong detached bow shock is formed ahead of a blunt shaped hypersonic body. For such a hypersonic vehicle, the drag is mostly wave drag due to the high pressure behind the strong bow shock wave. So, this is how a blunt shaped hypersonic body and a slender shaped hypersonic body would respond to the flow. In one case, for the slender body, the skin friction drag is going to be significant. In the other case, the wave drag is going to be significant. Low Reynolds number and high Mach number are basic ingredients of hypersonic viscous flow. High Mach number of course is evident, but we have not discussed about the low Reynolds number aspect of hypersonic viscous flows. Let us initiate the discussion on that aspect. Viscous dissipation and consequent heating. So, let us try to understand what viscous dissipation is all about and how is it connected with the aerodynamic heating. A hypersonic flow, it contains a very large amount of kinetic energy, and that is due to a very high free stream velocity. We are already aware of this. Now, when this flow occurs over a wall or a vehicle surface, it is slowed by the viscous effect which occurs within the boundary layer formed adjacent to the wall. So, when the flow occurs, all actual flows are going to manifest the viscous effect within a boundary layer which will be formed adjacent to the wall or the surface of the vehicle, where essentially the flow comes to a halt next to the wall. While within a very short distance, which we typically indicate as boundary layer thickness, from a 0 velocity to a very high free stream velocity, which we generally indicate by u infinity, is going to be achieved. And there are very large velocity gradients within this small thickness, and they are primarily responsible for loss of a lot of kinetic energy. So, when this flow occurs over the wall, the viscous effects which are responsible for creating these velocity gradients within the boundary layer and taking the flow to a halt at the wall, they are responsible for the loss of kinetic energy. The lost kinetic energy is transformed partly into internal energy of the gas, which would mean that this would also be responsible for the rise in temperature of the gas, because internal energy is inherently connected with the temperature of the gas. So, a rise of internal energy due to loss of kinetic energy basically means that the temperature is going to shoot up, and therefore, the boundary layer gets heated up. This mechanism or the process is referred to as viscous dissipation. So, the dissipation of kinetic energy due to viscous effects is what is called as viscous dissipation. This is a very important term in high speed flows. You have to remember it very meticulously. Now, you recall in an earlier lecture in week 1, we were talking about transition from supersonic to hypersonic flow, and we had introduced this parameter beta, where we said that it is basically a ratio of kinetic energy and internal energy, and if you put the respective expressions for it, this is how it will work out, and then here it is in a specific internal energy sense, and you replace it by the specific heat at constant volume times the temperature, and thereby finally come up with an expression over here which is dependent on gamma and the Mach number of the flow, the square of the Mach number importantly, which means this beta is going to increase quadratically with Mach number. As Mach number goes up, it is going to non-linearly increase. Of course, gamma would also have some bearing with Mach number. Even if you consider it to be a constant, you see a clear quadratic relationship between beta and m. Now, in compressible flow, there will be an interaction between kinetic energy and internal energy of the fluid particles. When the interaction is large or severe, it can cause the excitation of vibrational energy modes, dissociation, recombination, chemical reactions, and ionization of fluid molecules which are there in the gas, and this is another very major aspect of aerodynamic heating. We are going to discuss more of this in the later lectures, the reactions part of the flow. Now, due to the temperature rise, we are first interested to see how does the viscosity coefficient of the gas respond, how does it change with change in temperature. It is found that it increases with temperature. And if you recall the definition of Reynolds number, if you base it on the free stream properties, then you can define it as R e with a subscript infinity. It will be rho infinity, u infinity times some characteristic dimension, let us say c by mu infinity. So, we are talking about rise in mu infinity with rise in temperature. And how do we corroborate that? We can invoke an expression for the viscosity coefficient as a function of temperature, which is the famous Sutherland's law. And we are trying to understand what happens if the mu infinity increases. So, being in the denominator, that would mean that it will bring down the Reynolds number. If the Reynolds number reduces, then what bearing does it have on the thickness of the boundary layer? It increases the thickness of the boundary layer. Generally, we come up with relationships like this, where delta is proportional to 1 by root over R e. We have such a relation waiting here at the bottom of the slide. We will visit that relation a little later. So, it goes without saying that if mu infinity increases with temperature, then that will reduce the Reynolds number. If Reynolds number reduces, then the thickness of the boundary layer will grow. That means, the viscous effects will reach out further into the flow. And if you have a thicker boundary layer, correspondingly that means you have a smaller Reynolds number, and correspondingly that also means that in all probability the flow will remain laminar. So, we made a comment in the previous slide, if you recall, right at the top of the slide we said low Reynolds number, and that could also mean largely laminar flow. Now, with a thicker boundary layer here, we will try to understand the other implications in due course, but before we go ahead, let us have a quick look at the Sutherland's law. We will see it or visit it even later in the course. So, you have an expression for mu in terms of the temperature that exists at that point where you are applying it, and there are certain constants. You have mu ref, T ref, S with the respective units mentioned, and the mu, the unit of mu will come out to be kg per meter second, and then you clearly figured out that with rise in temperature the mu is going to increase. For air, it is approximately 0.71 over a wide range of temperatures. Now, since the pressure is constant in the normal direction through a boundary layer, it may not be exactly satisfied by hypersonic boundary layer, though. The increase in temperature results in a decrease in density through the equation of state. So, temperature rises, so that is in the denominator of this equation, and therefore, correspondingly it brings in a change in density, and that is based on the assumption that the pressure is more or less constant. So, there is a decrease in density, where of course, R is the specific gas constant for the respective gas you are talking about. Now, the mass flow through the boundary layer occurring at reduced density would lead to thickening of the boundary layer. Therefore, both these effects, that is viscosity increase and density decrease, in a combined way makes the hypersonic boundary layer grow more rapidly than at supersonic speeds. The flat plate compressible laminar boundary layer thickness usually scales using this equation, where it is proportional to square of the Mach number by under root R e x. X stands for the particular station at which you are looking at the thickness of the boundary layer. So, typically this delta is also at a particular location x from the leading edge of the flat plate, for example. The thick boundary layer in hypersonic flow produces a strong displacement effect on the inviscid flow which lies beyond the boundary layer. So, there comes a very strong displacement effect. Now, as you know that when the flow is developing on a flat surface like this, This is the boundary layer thickness. This is how it is growing gradually. You can also calculate the displacement thickness corresponding to this boundary layer, and basically that is of a lot of significance in terms of figuring how far does the boundary layer flow displace the outer inviscid flow, and that is precisely what is emphasized in this point. A large displacement thickness causes a given body shape to appear much thicker than it actually is, because the body shape, if I define it as a y equal to f x kind of a functional form, then when it is immersed in a viscous flow, the y as it appears to the flow would not be f x alone, it would be displaced by an amount of this order. So, there will be a displacement thickness adding on to the geometric shape of the surface, and that displacement thickness of course is also a function of x, which is basically the length from the leading edge of the body. So, it appears thicker than it actually is. This alters the outer inviscid flow. The changes in the inviscid flow in turn feeds back to affect the growth of the boundary layer. The significant interaction between the boundary layer and the outer inviscid flow is called as viscous interaction. So, this is basically interaction between boundary layer and outer inviscid flow. Viscous interactions, how do they affect? They are responsible for affecting the surface pressure distribution on the vehicle surface, and consequently, if you integrate an altered surface pressure distribution, you will see change in lift, drag, pitching moment, and therefore stability of the vehicle. It enhances skin friction and heat transfer. The hypersonic shocks, which are known to be formed very close to the body, in this context you may recall the other day we were talking about the beta to be of the order of 1.2 times theta in the limit m1 tending to infinity, which basically indicated that the shocks form very close to the body. Therefore, hypersonic flows are characterized by thin shock layers. Now, when you have a thick boundary layer forming on a hypersonic vehicle and it becomes so thick that it may merge with the shock wave, in such a case the shock layer can neither be treated as inviscid nor comprised of a thin boundary layer followed by an inviscid portion of the shock layer, because the shock layer should be treated as fully viscous in that case. So, what we are talking about over here is that if you have a situation like this, that there is a body immersed in a hypersonic flow and you have a very thin shock layer between the shock and the body, while you have a significantly thick boundary layer forming on the body, then it may so happen that you do not have the shock layer in the inviscid form anymore. So, even the inviscid equations that we use to analyze the shock relations and so on becomes questionable, because it is highly affected by the viscous effects of a much thickened boundary layer. This of course, is shown in a highly amplified manner, where the boundary layer thickness is way larger than the shock layer, but the point we are trying to make over here is that they could be of the same order. From altitude velocity map, we can show that laminar flow occurs at higher altitudes and turbulent flow at lower altitudes. So, what are these altitude velocity maps? We are going to visit them in detail in some of the later lectures. So, when we look at re-entry bodies typically re-entering the Earth's atmosphere, it moves through the entire thickness of the atmosphere till it comes and lands on the surface. So, this altitude could be of the order of 100 kilometers or more, and the velocities are much higher at that 100 kilometers altitude or a little more, and it comes very close to 0 by the time it touches down, which means at the higher altitudes you are having much higher velocities. the velocity is reduced as the altitude reduces, and therefore, you could generate altitude velocity maps. And through suitable calculations, we can argue that mostly laminar flows would occur at higher altitudes and turbulent flows would occur at lower altitudes. Now, aerodynamic heating at high Mach numbers occurring at high altitudes and consequent reduction of Reynolds number, which is due to low density and high viscosity, has already been discussed. We shall subsequently discuss about the laminar boundary layer form of the viscous Navier-Stokes equations for a flat plate. Using the boundary layer solution, we shall study the effect of the free stream Mach number and wall boundary condition on the boundary layer thickness, the temperature profile within the boundary layer, and that is for two different kinds of thermal boundary conditions, namely isothermal and adiabatic wall boundary conditions. So, for that we have to of course derive the laminar boundary layer form of the viscous Navier-Stokes equations, which we will take up soon, and we will confine it to the flat plate case. We shall briefly discuss results for stagnation point flow relevant for blunt nosed hypersonic vehicles. However, we will not derive them, we will only look at the final results. These are familiar equations which you have learned in an earlier week, but it is a good time to revisit them again. So, since we are going to discuss about the continuity, the momentum and energy equations once more over here in the context of the compressible Navier-Stokes equations and those being reduced to the boundary layer form and so on. A quick recapitulation of those equations. So, here is your continuity equation, here are your momentum equations, this is your energy equation and the respective flux terms indicated, and here we of course have considered the Eulerian control volume framework, and therefore, you have fluxes A to J respectively covering the three important conservation equations. You have here the equation for sigma ij, the tau ij term of the sigma ij. Of course, we will continue with the Newtonian fluid assumption, the expression for the energy term which figures in the energy equation, and a detailed description of all the fluxes. Now, again you may recall that we had a lot of forms. Here when we look at the next few slides, you will see that we would prefer to go ahead with the infinitesimal fluid element approach rather than the finite control volume approach. The finite control volume approach we have used for the shock wave equations, for example, but here we prefer to do the analysis with the infinitesimal fluid element, and therefore, we are going to use the derivative forms, and of course, we are going to take an Eulerian perspective of that. Some of these terms will not be relevant for us, which we will discuss in due course. For example, we are not going to consider body force terms. Looking at momentum equation to begin with, you may be wondering why we did not look at continuity equation, because I would like to give that as a homework problem for you. So, here we are again simplifying the momentum equation. First of all, we are looking at it as the x component instead of all the components represented in a compact manner through the indicial approach. Here we are splitting them into components and trying to analyze them. We are going to assume the flow to be steady, two dimensional, occurring in the xy plane, of course viscous, compressible, and written in a differential form, which I already mentioned. Additionally, we are going to neglect the normal stress component sigma xs and the body force terms. The sigma xx term may not be so very relevant for us over here, especially in the boundary layer context, and therefore, we are keeping it simple. As a consequence, you may recall that this is connected with your sigma xy, and therefore, the dimensional form of the equation will look like this. Now, we would like to non-dimensionalize it, and for that we introduce a couple of non-dimensional terms, as you can see over here. So, rho dash defined as rho by rho infinity, u dash as u by u infinity. So, we are using the free stream values here for non-dimensionalizing these parameters. Additionally, as far as the length scales are concerned, we are using a particular characteristic length scale, which you may say is like the length of a flat plate. Or a chord, if you wish to mention it that way. Now, if you substitute these non-dimensional terms, you will end up getting the non-dimensional x momentum equation. So, they are written in terms of the dash terms. Additionally, there are some coefficients associated with the pressure gradient term and the viscous term that you can see on the right hand side. Now, if you look deeper into these terms, you find that the P infinity by rho infinity u infinity square coefficient associated with the pressure gradient can finally be represented in the form of 1 by gamma m infinity square. Gamma, of course, is the ratio of specific heats. The m square, which is basically the square of the Mach number, the free stream Mach number. What is it indicating? It is basically proportional to kinetic energy of the flow versus the internal energy of the flow. And the Reynolds number, which shows up from the coefficient associated with the viscous term, of course, as 1 by R e infinity, that, as we may recall, is a ratio of inertia force and viscous force. Therefore, we introduce these terms here in the coefficients. These are called as the similarity parameters. So, if we are considering two flows, for example, which are identical in terms of gamma, m and R e, and additionally the two bodies are geometrically similar, then the two flows are considered to be dynamically similar. Thus, the gamma, m infinity and R e infinity are called as the similarity parameters because they bring in the similarity between the two flows in addition to the geometrical similarity. Now, as I mentioned earlier, following this approach, you should be able to derive the non-dimensional continuity equation, which is indicated here. Additionally, you should also be able to work out the non-dimensional y momentum equation. As you can see, the coefficients which we saw for the x momentum equation come up over here even in the y momentum equation. However, as far as the continuity equation is concerned, there are no such collection of terms. Again, these collection of terms, of course, are non-dimensional. If you look at the energy equation, for example, the energy equation shows like this. We are neglecting body forces, we are neglecting the volumetric heating, and we are also neglecting the normal stress terms sigma xx and sigma yy. Heat transfer through thermal conduction is considered. So, if you bring in all these aspects, additionally remember we also have the assumption of steady flow, which means you will not have a time dependent term on the left hand side. So, then you have these two terms on the left hand side followed by the conductive heat transfer terms and the additional terms on the right hand side involving the stresses. So, now if you in addition to the non-dimensional terms which we had earlier introduced, bring in some more non-dimensional terms in terms of the internal energy, in terms of the square of the velocity and thermal conductivity and temperature, then you should be able to non-dimensionalize each one of the terms of the energy equation. So, if you go ahead with that process, then the energy equation first can be non-dimensionalized like this, where you will have a couple of coefficient terms coming up over here, and then you should be able to finally convert them in terms of some coefficient terms involving set of similarity parameters, where a new important similarity parameter will join, which is called as the Prandtl number. It is nothing but the energy dissipated by friction divided by energy transported by thermal conduction. It is proportional to these two effects, and Prandtl number happens to be a property of the gas. It is different for different gases, and for non-reacting gases it is a function of temperature only. For chemically reacting gas, it is dependent on local chemical composition. So, we will revisit the energy equation once again in the next lecture. Just to recapitulate, now in this lecture we discussed about basic concepts of viscous compressible flows. We started discussing the governing conservation equations. Thank you.